Dr. Alex. Okay, we invited Dr. Alex Chiplinkin. Did I pronounce your last name right?
That's good.
Okay, and from Graphcore to teach this course. Alex is the director of field AI engineering at Graphcore, and he's an expert of AI ML and Graphcore technology. So let's welcome Alex for today's teaching. Thank you.
Thank you very much, Jennifer, for introducing me, and thank you very much, everyone, for joining today. As stated on the web page of this course, we'll spend the first about 30 minutes giving a brief introduction of the IPU architecture and software overall. Then we'll have 3 hands-on parts, making sure you have access to the platform and the system, and you can run examples there. And then a deep dive on TensorFlow and PyTorch running on IPUs. We'll take a short break, maybe halfway down the road. And please feel free to ask any questions as we go. And I will be very happy to keep this as interactive as possible. So the agenda was covered. The hands-on parts will also be included in the sessions today. A couple of words about Graphcore. We are more than 7 years old as a company, over almost 500 people. Graphcore has created the IPU Intelligence Processing Unit, targeting at training and inference, machine learning training and inference in data centers. And we have offices around the world, and we've raised over $700 million from some renowned investors shown here. Given the mission of the company to enable new breakthroughs in machine intelligence, the architecture of the IPU is quite different from GPUs or CPUs. We have a true MIMD processor, multiple instruction, multiple data, with all the cores, all the threads on the processor being independent when running in parallel with each other. And this gives a lot of flexibility when implementing machine learning kernels. For example, we can extract more parallelism when running at batch size 1 for lower latency inference, for example, or lower batch size training. This is big difference number 1 in terms of the architecture. And in terms of memory access, we have a large amount of SRAM on the chip, and it is distributed throughout the chip. There is no shared memory or memory hierarchy, actually. Every core on the chip has SRAM associated with that core, about 638 kilobytes of SRAM per tile, as we call it. And the bandwidth between the memory and the compute on the chip is very high. It's 64 terabytes per second. And with this bandwidth, we can move weights or activations from memory to compute units faster and achieve higher throughputs for machine learning. And this can be compared to GPUs that are SIMD machines with warps of threads running the same operation on large vectors of data. So GPUs are designed for large blocks of dense contiguous operations on vectors. And GPUs has a large amount of HBM available at a lower bandwidth. So we are enabling a different spectrum of problems with this IPU architecture. And CPUs are designed for scalar processes. So, and they are adding some SIMD vector operations or even matrix-based operations recently in AVX, for example. The IPU has been used successfully across the board in terms of the different research domains and use cases, healthcare, finance, NLP, computer vision, computational chemistry, weather forecasting, and lots of others. So overall, the guidance to use the different IPU architecture can be as follows. We are seeing great performance on different gather-scatter operations that are important for GNNs. And this is because of the MIMD and memory bandwidth advantage that we have. Some finer grained kernels like depth-wise separable convolutions run faster on the IPU, and EfficientNet is based on that. Some vector operations like matrix vector multiplications that have lower arithmetic intensity in terms of the number of flops per byte fetched from memory. Dense and sparse metmols, random number generation, which is hardware accelerated on the IPU, so you can generate random numbers very quickly and efficiently. And workloads that are hard to vectorize, and DFT, density functional theory in computational chemistry, is an example of that. Other workloads that can be harder to vectorize include something like ray tracing, where each thread would execute an operation till convergence, so different threads would achieve convergence at different points in time, potentially. Options pricing and DFT, where physically every thread needs to execute different sets of operations, sets of instructions. Maybe somewhat similar to that, tree-based models with trees that are different sizes, different depths, different shapes as well, unbalanced trees. As one of the examples of that, we have recently open sourced an implementation of PySCF targeting IPUs, and you can feel free to access that among our public repositories on GitHub. Specifically, you can run those notebooks either locally on the Texas A&M system in ACES, or you can run those in Paperspace, which is a small cloud similar to Colab. And the DFT notebook would produce a picture like this. And the bigger idea is to enable drug discovery by some of the pharma companies, which currently mostly run on CPUs and thousands of CPUs, but those can be replaced with a small number of IPUs. The essence of the DFT computation and why is it a good fit for IPU is twofold. One is this computation of the E matrix, which is quite large, and every element of this matrix is a set of operations with lots of ifs or with a switch statement in it. And it's really hard to vectorize. But on a MIMD processor, we can leverage the independence of the threads and efficiently compute this matrix. And the second aspect, the second part of the computation is an iterative process that you would do for maybe 20 iterations, as in this case, which is a vector matrix multiplications, as shown here, which are memory bandwidth bound. You can do that on the CPU, but even if you have a lot of flops on your processor, you will be moving as quickly as you can stream the data from your DRAM. On the IPU with SRAM, it can be executed much faster. And we are seeing some nice speedups for DFT. And DFT is kind of outside of the realm of machine learning, but I wanted to just bring that example up to highlight the difference of the architecture. This is the high-level floor plan of the IPU. And you would see that here, red squares are compute cores, and then the rectangles are memory associated with every core. So every core has local and private SRAM. Overall, we have 900 megabytes of SRAM, 65 terabytes per second to that from the compute. 1,472 cores, each core running 6 threads in a round-robin fashion, so almost 9,000 threads. And the compiler, say if you are programming in TensorFlow or in PyTorch, the compiler will try and map each operation to all the available cores on the processor. So a matmul would be distributed across all the available threads and cores to extract as much parallelism as possible and reduce the overall number of cycles an operation takes. And this is different from some other architectures, data flow, maybe architectures as they are called, where a subset of cores would be dedicated to an operation, and then the data will be streamed to another subset of cores, etc. In our case, we are trying to leverage the entire chip. We have external connectivity for the chip provided by the IPU links. And with these, we can enable additional parallelism across the chips, such as pipeline parallelism, tensor parallelism, or data parallelism, or some kind of mixture between these three. And we connect to the host through PCIe. A small detail in the generation that we have in the ACES Center of Texas A&M University. We have this bow version of the IPU processor, and it employs the wafer-on-wafer technology, where we actually bond 2 wafers together, one being the power delivery wafer and the other being the logic die. And with this power delivery wafer, which is full of basically capacitors, we can run at a higher clock rate while being more energy efficient. And this helps us run up to 40% faster without any changes to the software at all, purely by this hardware wafer-on-wafer change. And this is the first processor productionizing this technology. The computation on the IPU is structured using so-called bulk synchronous parallel paradigm. At a high level, this means that the cores on the IPU will be executing a sequence of alternated data exchange and compute phases. And those map really nicely on a computational graph, as, for example, shown here, where we have some input tensor slices that are used by some compute vertices, some vertices in the computational graph that perform operations, and those vertices would produce some outputs. Those outputs in their turn will be used by another compute vertex, and so on. So these are structured on the processor as data exchanges between the cores and then computation phases, while all the cores run on the local data. And there are synchronization phases between after each compute phase and before the exchange phases. To depict that maybe more intuitively, or to build more intuition around that, I am showing different cores as horizontal swim lanes on this slide, and then compute phase is shown in red. So during the compute phase, all the cores will run independently from each other, no data exchanges between the cores, so they operate purely on their local SRAM. And then at some point, they will finish the computation and will synchronize between each other. At this point, we'll have the chip in a deterministic state. We know what has happened and what needs to happen during the next compute phase. And we are able to move the data between the cores so that if a slice of a tensor was produced on this core, it will be moved to another core, to the SRAM of this other core, where it will be used for the next compute phase, for the computation there. So this is done during the data exchange phase. Data exchanges on the IPU are scheduled statically, and that means that the graph is compiled typically end-to-end with potentially some end-to-end optimizations there. And we need to know the shapes of the tensors during the compilation time. So this, in some cases, requires us to do changes to the program, maybe adding padding to sequences or to graphs. So this is on the execution scheme. And again, please feel free to turn your microphone on and ask any questions, or do that in chat. On the hardware side, this is what a both IPU 2000 machine looks like. And the systems in ACES are built using these machines as building blocks. Each Bow IPU 2000 has 4 IPUs in it, connected together with IPU links. And IPU links are going out of the box to connect several blades like this together. And we have host connectivity delivered by this NIC card. So this is a disaggregated system. The machines that you will be SSHing into and running your Python scripts on is a separate machine, a CPU-based machine that connects to Bow 2000s through Ethernet links, 100 gig Ethernet links. The topology of the IPU links between the IPUs is shown here. So this is a single Bow 2000 box, and the IPU links are shown in red. And we connect multiple chassis together like a daisy chain. So overall, it looks like a ladder for a pod 16. And Texas A&M has a couple of pod 16s in the data centers. So the IPU links connect chassis to each other, adjacent chassis as shown here. And this is the host to accelerator machine links that are used to stream data during training or inference, get the results back, and upload binaries for the IPUs to run. Now, the hands-on part that I wanted to get to will be described by the commands in this document. So if you can, I would encourage you to open this link. So bit.ly/tamu, then today's date, 23/10/03. And if you open this document, you will see something like this. And you will have the rights to comment on this document. And if something is not working, please let me know. I've tested it yesterday and it was working fine. But something can go wrong as it happens during demos. So the steps to get access. Thank you. The steps to get access to the system are shown here, and basically you can navigate to this portal, which would look something like this. You will need to be logged in using your Access account, which was mentioned as a prerequisite to the course. On this page, you can go clusters and shell access, which will open a terminal window as such. And I think this is the right time where I kindly ask Zhenhua to provide additional guidance or say more words.
Yes, Alex. I think, can you hear me?
Yes.
Okay. I'll share my screen. Actually, oh, I'm sorry. I think I logged in with my Gmail account. GR3, can you enable share screen for me? I think I'm not on my time of Zoom.
Okay, yeah.
Oh, thank you.
Can you share now?
Oh, yes, thank you. Let me find my, I think this is the one. Can you see my screen?
Yes, Senra.
Okay. So this is about how to access ACES. So we usually use the access portal to access the ACES cluster. So whenever you get to our website, TestCNM High Performance Research Computing, there's a portal tab here. At the bottom of this menu, you will see the access portal access. And ACES portal is a web-based user interface for ACES cluster. So after you click on the ACES portal, you will be able to open this. After you open this, you will have to do authentication via CR logon. So as an access user, you can select access CI exceed as your identity provider. And this will, after you click on log on, you will be directed to here. And you will need to type your access username, access password, and then click log in again. After that, you will see very similar like Alex web page. So you will click on clusters. So you will see the ACES shell access. Click on that. That will give you the terminal. So and in the terminal prompt, actually, you will see your login node. Like for ACES, we have I think 3 login nodes for access users. If you have logged into ACES, you can type your, let's do some participation. Like if you can type your login node number into the chat, so that we know that you have successfully logged into our ACES cluster. So please give us, okay, we have Paul on logging 3. Okay, Justin on logging 1, the first logging node of the others. So let's give like 1 minute or two to finish the logging. If you have any questions or problems accessing the ACES cluster, you please let us know. Okay, we have 1, 2, 3 logging nodes 1, 2, 3 now in the chat. Poplar 2 works. Yes, Poplar 2 works, and I guess today we are going to use Poplar 1 for the examples, right, Alex?
I think Poplar 2 should behave identically.
Yes.
Will be using Poplar 1.
Okay.
For me.
But for some of the local data directory, probably I guess I'm not sure Poplar 2 still have the local data directory or not.
Okay, no problem. It's
okay.
not
If you
requirement.
If you encountered any problems on Poplar 2, because actually we are using the raster file system on Poplar 2, so it could behave a little differently. But if you encounter any problems, and you can let us know, and also you are welcome to switch back to Poplar 1.
I cannot log into Poplar 1 prompting me for password, but I can log into Poplar 2.
That's interesting.
That might be my account has been using the last 2, 3 the tutorial, so I'm not sure if that.
Oh, okay.
But I can log into Poplar 2 if that is okay.
Okay. Okay, you can try that, but we will see. Okay, I think Poplar 1, Poplar 2 both work for me. Okay, if you have any questions, you can let us know.
My guess
Poplar
would be
1.
that the users on the Poplar 1 might be set up to use a password when SSHing into the system, while maybe Poplar 2 can be configured differently. So it's a configuration thing.
Okay, let's continue if we can see any difference, or it's good for testing.
So
okay, what?
Was anybody able to SSH into Poplar 1?
Can you guys give us a thumbs up if you can SSH to Poplar 1?
I see. Looks like
yeah,
all the accounts were created with a password. Is anyone having issues SSHing into Poplar 2 instead of any Poplar? So Poplar 1 or 2.
Do you want to try Poplar 2, Alex, since most of them are on Poplar 2?
Yeah, I can SSH into Poplar 2 as well.
Okay, that's great.
Okay, then I think a good thing to try will be running those few commands till what? Well, till probably running that example there, and then I will be sharing some background information about the software stack. And let me also try to use to run the GC monitor command. Looks like I can do that. Let me share my screen again. Permission denied on Poplar 2 when making that directory. Interesting. Okay, so I have tested these commands with Poplar 1. Let's see what happens on Poplar 2. First of all, the two commands here, the source Poplar SDK, sourcing the enable script here, and then GC monitor. The first command sets up some environmental variables on the machine so that IPU specific tools are used.
Alex?
Yep.
They have a permission denied to the local data directory, right? They cannot create the directory. How about we change make a directory to their scratch?
To the home, you mean?
Yeah, like make directory -p $ scratch/tmp scratch.
Let's see. So that would be
dollar.
Should it be in the home directory?
I think a scratch directory is better. So
like this.
Scratch. Yes. And SCR.
Is it capitals or small letters?
Capital. SCRATCH. Yes. I think everybody, can you try this? Change the local data /$user to $scratch for the commands.
Okay, nice. So let me update the document accordingly.
Okay. Yeah, change the local data. Yes.
So that should work. We are not using TMP anywhere else. Okay, so apparently in my case, I was able to create that directory and move forward. We do not need local data anymore. And thank you for the real-time feedback, everybody. Now, after I source the SDK with this, the enable script of the SDK, I have access to IPU specific tools. Most of them start with GCC-something, and then GC-something. GC monitor, which stands for Graphcore monitor, shows the available IPUs on the system. And you will see 16 of the IPUs here. And if there is a job running and using an IPU, it will be shown here in the outputs of GC monitor. And you should be able to see who is running the job, what's the process ID for that job, and some other parameters of the execution, for example, the temperature, the power consumption of the IPU, etc. And let me execute the following commands. So these two exports of the TMP that we've done, they set up directories to cache compiled binaries for TensorFlow and PyTorch, so that when the compiler executes something that has been compiled and cached previously, it will just load it from cache. It will load the binary from cache instead of compiling it again from scratch, which can speed up the runtime overall. The following two exports are optional, and I have basically commented them out here to show it. If you export these variables with the info value in those, the outputs of the compiler will be movables, and it's not required. It's probably good when you want to get a better feeling of what's happening under the hood when you're running things here. Let me try and enable those just to show you how it looks when it runs with these variables on. And then just again to make sure all the commands are executing correctly on the Poplar 2 server, let me do a pip installs as well as shown in this document. So these 3 pip installs take the wheel files for TensorFlow, for Keras, and for PyTorch from our SDK package, from Poplar SDK. And as you might have guessed already, we call our software stack Poplar. And this name is based on a neighborhood of London where the creator of the first fully electronic computer lived about 100 years ago. So while it's being installed, it looks like
it looks like
a message that I do
you
not.
said that it says quota exceeded, right? So can we change the home directory to scratch directory? CD when you prepare the Python virtual environment, can we CD scratch? Yeah. And because the home quota is very small, the space is very small, and we want to
okay.
Yeah.
Sorry about that, everybody. I did not test the scripts on the Poplar 2. So I need to delete this virtual environment and then we do everything using the scratch storage instead. Please do not forget to deactivate your virtual environment before deleting its directory. So it looks like I was able to successfully install TensorFlow and Keras. And moving on to PyTorch now. Yeah, this is a good correction. Let me set this thing up here. The install succeeded in my case so far. Let me, as a kill, corrected the document, change directory to that scratch folder directory, and then move forward with the example as shown here. So I will clone the examples repository on GitHub. And Graphcore has quite a few public repositories that you can take a look at, including the libraries, Poplar libraries that we use. Nice. Thanks, Joe. So those Poplar libraries are used throughout the software stack. They have operations like matmols and element-wise operations for neural networks like nonlinearities, etc. If you would need to build something, maybe a custom op in PyTorch or for TensorFlow, please feel free to take a look at those at Poplar libraries in our GitHub. And the policy of open sourcing our software that we're taking is quite different from some other vendors like CUDA, CUDA libraries are not open. So I'm running the example right now for the simple MNIST training, as you can see here. And in this green color, you can see the verbose outputs of Poplar and Poplar libraries as the driver, in this case, loads the binary onto the IPU and executes it. So this is an important milestone, and let's use the following 15 minutes to make sure everybody can run an example as mentioned in the document. And thank you everybody for the corrections and suggestions to the document itself. It's a collaborative work now. So no need to run it with profiling. You can do it, of course, but it's optional. What the next line in the document will do, it will run the same example, and it will produce a profile in the directory here that can be used later by the pop vision tools that we have to understand what's happening when we execute the program, where the cycles are spent, basically. We'll touch on that a bit later during today's workshop. So in my case, the example ran successfully, and please let me know when you get here and if something is not working properly for you. And I will spend the next 10 minutes or so running through the rest of the slides for this part. Thank you, Dave. Happy to hear that you are running successfully. So Graphcore has this developer web page. If I go to the Graphcore website, and let me make it full screen again. So in the developer section here, we'll have a bunch of useful things. Documentation, model garden, notebooks, pointers to different GitHub repositories, including tutorials, Slack community, other resources like videos, webinar recordings, research papers, white papers, pop vision tools, and downloads that you can download without any account created. It's all open for you to use with a wget or curl command from the system itself. So I encourage you to navigate and explore. And we've been getting very positive feedback in terms of the documentation that we have. Almost all the questions can be answered by running a search here, or since everything is open and indexed by Google, you can do something like Graphcore PyTorch optimizations, and you should be able to quickly navigate to the right section, the right API in the right document, basically. So this is what I wanted to show you. And in the GitHub, we have quite a few repositories, including the TensorFlow, the poplibs, and different algorithms. Graphcore research community has several algorithms that are quite helpful. For example, there is what we call IPU tessellate, which is somewhat similar to OpenAI's Triton, and it allows you to program the IPU at a tile level using Python commands and JAX. So that's quite an interesting tool, I think. gives a lot of flexibility and control over what's running on the tiles there. And I've mentioned already white papers and webinar recordings that are available. This slide shows the overall software stack that gets you from notebooks and high-level frameworks here down to the drivers and runtimes. And it goes through XLA in terms of TensorFlow, in case of TensorFlow, and then through PopArt, which stands for Poplar Advanced Runtime, which is used for PyTorch. So the computational graphs for TensorFlow would be extracted using XLA and then brought down to Poplar libraries, which then schedule the computation across the tiles on the processor. And in case of PyTorch, the computational graph is traced and extracted with PyTorch dispatcher. And in this intermediate representation, it goes down to PopArt, Poplar Advanced Runtime, which then maps it to Poplar libraries. And at the level of Poplar libraries, we have Graphcore Communication Library, which takes care of parallelism of data exchanges between accelerators, basically. And the lowest level Poplar framework, which you can use programming in C++ at the lowest level, and you'll have full control over what's happening on a given tile at a given step of the program. And around this core software stack, we have examples of different applications, tutorials, documentation, different profiling tools that we call overall Pop Vision tools, Poplar Vision, and then some monitoring and orchestration tools like Kubernetes and Slurm that are supported. And we'll be using later today, well, in a few minutes actually, tutorials, which are a part of the examples repository on our GitHub. Should you have any specific machine learning model, any architecture or use case, please feel free to navigate to the model garden here, which actually is a part of the same developer webpage. So I go to this link and I can use this filtering panel on the left to maybe select all the PyTorch applications for natural language processing. And with this, I will be able to find a model, an example that is the most relevant to what I'm trying to do, and start with that one. For example, GPT-2 large training. I can navigate to the repository there. So notice that I am in the Graphcore organization examples repository. Then the structure is NLP, which is machine learning domain. In this case, model name, framework name. And for every example, we have a README file, which has some kind of description of the model, and it includes the steps to reproduce a benchmarking number, for example, or to run this model in different use cases so that you can predictably run an example without thinking too much on how to get there. So overall, this should give an easy start to most of the work you will be doing, hopefully. Hopefully most. I mean, hopefully we have a good coverage there. And we have a lot of one-click kind of notebooks ready to use on Gradient, which is a part of Paperspace. Gradient is an environment similar to Google's Colab. So a notebook-based environment, a Docker running on a VM attached to IPUs. So if you click on a button like this in, say, in the model garden, you will get to the specific notebook, and then there will be a button to start the machine. You will need to create an account on Paperspace for that. And the final slide for this part talk about the environmental variables. And many of these we have discussed already. So logging can be enabled for multiple components of the software stack. For example, Poplar log level can be very verbose, like incredibly verbose with trace as the value for the variable. Info is already pretty verbose, and then off is the default. So, Jay, now looks like the error you are mentioning in the chat can be due to the absence of the variables or environmental variables that are set up using this enable script. So if you would try and run this line before running the example, I hope this will help. Throughout your journey with IPUs, please feel free to either shoot me an email directly or join the Slack channels that ACES has. There is a channel for Graphcore there, or the Graphcore community as well. So it looks like most.
I think Li Jingzhan, you registered this morning at 11, about 11. So our system admin, yes. So we are trying to add you now.
Okay. Yeah, sorry for
So,
registering it late. Yeah,
no
so
problem.
I did register it like kind of before the meeting. So
okay, no problem. And we are adding you now. So I will let you know if you can also try. And I think our system admin and our staff are doing the work now.
thank you so much. Sounds good.
You're welcome.
Mm-hmm. Thank you, Jean-Paul. So other environmental variables include the report creation, which is done with Poplar engine options. Auto report equals to true. Executable cache, which we have in the document for PyTorch and TensorFlow. And there is an option for TensorFlow to use synthetic data, meaning the data will be generated on the IPU, so you can benchmark the execution without any host activity. So there is no I/O, no data preparation on the host, purely the engine running on the accelerator device. This is helpful to see if host is a bottleneck for the execution. And we have, of course, a document describing all the command line tools. Some of them are listed here. The most useful ones would be GC monitor and GC info. And GC info can give you a list of all the available devices on the system, IPU devices. In this case, we have 16 IPUs that can be targeted as individual accelerators, as shown here, or you can request IPUs, multiple IPUs in powers of 2. So you can request a device with 2 IPUs or 4 IPUs or 8 IPUs or 16 of those. Those will be allocated based on the locality. So you will get a slice with the IPUs that are connected, optimally connected to each other. So, and this is everything that I had for this part. The following part, after, I guess, a 5-minute break, will cover TensorFlow 2 and Keras, how to port those to the IPU, and we'll be using tutorials for that. And the final section will be dedicated to PyTorch. Similarly, we'll rely heavily on the tutorials that we have in the public repository, which is available. So if I go to the examples repository here, I will, instead of NLP, dive into tutorials like this. And we'll start with this TensorFlow 2 Keras tutorial. And now I suggest that we take a quick comfort break for 5 minutes, if Zhenhua, you agree with that.
Yes. Jerry, can you post the break slide?
Yeah.
5 minutes. We should be back at 2:40,
Yep.
I guess. Okay. Thank you.
Thank you very much. And I will pause the recording. Welcome back from the break, everybody. Just wanted to make sure I address the situation that Jinal pointed to, where he was getting this error. The SDK was not unable to import PyTorch. The most likely reason for that is that when you SSH into the system and you do not source the enable script, so I skipped this command. And these are kind of secondary, but let me do that anyway. And then I activate the virtual environment. I have everything installed there already. And I try to run the example like this. In this case, I will not be able to import PyTorch successfully. So this command will generate that kind of error, unable to import PyTorch. And to solve this, I can source the SDK 3.3 enable script. With that, it should have all the paths corrected, and the example will run. So, Janel, please let me know if and when you are able to run this. And thank you, Akhil, for suggesting this in chat. So, getting back to the agenda, Keras and TensorFlow 2 can be used on IPUs, and Keras probably is the most popular API if we're talking the TensorFlow world there. So we have a couple of classes in Keras: model and then sequential, optimized for IPU. Sequential just allows you to list all the layers in the model that are then chained together to process an input. Model will enable what's called functional representation of the model, where you specify inputs and outputs, and then it would build the graph accordingly. The IPU optimized part includes what we call on-device training loop, gradient accumulation, and some data parallelization strategies. For example, we can run with multiple replicas really easily on the IPU. And let me explain what are these and how these techniques help us increase our throughput on the IPU and run faster. So we start with the simple example with a GPU script Very simple one, training a CNN on the CFAR10 dataset using standard SGD optimizer. So this GPU script is on the left and the IPU script is on the right. The differences are shown here. The first line is importing the IPU specific Python module. The following 3 lines allow us to allocate a single IPU, the first one available basically for us. So the stack Poplar will try to see which IPUs are available and will try to attach to the first one available here. And it happens when we configure the IPU system here. So with this, we have created a TensorFlow device, which is then used in the following line, the IPU strategy scope here, with the statement, which basically tells TensorFlow that this computational graph has to be put on this TensorFlow device, on the IPU basically. And these are the main changes to the code that you typically would need to do. An important thing that I have here, not very clearly visible, is this drop remainder parameter when batching the data, creating the data set. It ensures that we do not have a tiny tail, an incomplete batch when producing batches out of the data set. And this kind of small tail batch would mean that the shapes of the tensors that we have compiled with have changed now. The last batch will require, if we didn't do this drop remainder, will require special compilation for the program. So it's cheaper to make sure that we have, an integer number of samples that we used to train our model on. So let me see what we have in the chat. Great, so Jinjan is able to work with the system. And JNL is getting permission denied with the Pop Vision Graph Analyzer. So we will get to the Pop Vision tools a bit later, but it would be worth figuring out permissions up front, I agree. So in the tutorials, you can see that, so if you open this link, and this link is also a part of a document that we have. This link specifically. So I have opened this one here. And I have navigated to TensorFlow 2 Keras here, which has some basic examples. So the README file mentions most of the details that I have already covered on that slide. And I will just go through these one more time. This is the initial script. Very similar thing, but in this case, we build the data sets more explicitly. We produce NumPy arrays with a training, X and Y values, and the test portion of the data set. When we have the dataset creation done explicitly like this, we will have to make sure that the data set length is divisible by the batch size more explicitly. And this is what is done in this Keras tutorial. Then in the initial script, we have the model built using this function here, the computational graph, and then the Keras model class is used to instantiate the Keras model, which is then compiled with SGD as the optimizer, some loss and metric for the training runs. Then the script executes the training itself for 3 epochs, and we run evaluation after that. The changes are described, changes when porting the script to the IPU are described in the following sections of the README file, which are making the dataset length divisible by the batch size by simply dropping the remainder, basically, of the dataset. And then allocating the IPUs. In this case, it offers as an option this on-demand allocation. And that means that instead of grabbing the IPU right away, including during the compilation, it will attach to the IPU only when the actual execution happens. So the IPUs will be available for other users more time. And then we instantiate the IPU strategy that is then used to tell TensorFlow that it needs to put this graph on the IPU as a TensorFlow device. Now, these are kind of the basic changes, and you should be able to run this example if you navigate to that directory and see as the output something like this with this time per step. And let me try and do that as well in real time. So I go to an upper level and maybe one more level up. In the tutorials folder, I will go to tutorials instead of simple applications, and then TensorFlow 2, Keras. So there will be the starting point here, and feel free to examine that script as well, which is basically the CPU or GPU code. And the example that we are interested in would be among the completed demos, completed demo underscore IPU, which has this basic set of changes to start running on the IPU in a not in an optimal way yet, but it should be already running on the IPU. So I changed directory to completed demos like this, and then I should be able to Python completed demo IPU to run this thing. Let me see if there were any requirements necessary for that. So we should be fine. And now it goes through the graph compilation, which takes under a minute, typically, for small graphs. For very large graphs, like GPT-3, it would take maybe 20 minutes. And if something takes more than 20 minutes to compile, please let us know. That's an anomaly. So we were able to run on the IPU in this case, and it's taking 2 milliseconds per step. Let me see if I skipped anything in the README file. So we are about here. So we should be here, and the following timings that I have looked at, the 170 microseconds, relate to a script that has an optimization in it, which is this steps per execution in the model.compile. This parameter or argument, steps per execution, is a part of the standard Keras framework, and it's useful for TPUs as well and other accelerators. What it does, it makes the accelerator process more than one batch of data and do several gradient steps every time you call the model, every time you execute the engine on the accelerator. In this case, for example, we have this demo faster script, which uses steps per execution, and we use some kind of number for the steps per execution. In this case, we're trying to process the entire data set during a single engine run. So with a single run, I will process all my batches, do all the gradient steps, the entire epoch, without getting the control back to the CPU. And with this, I can avoid the overheads of starting the engine on the IPU, preparing the next batch, streaming that next batch to the accelerator. This overhead will be reduced and amortized across the multiple batches that we have. So if I try and open this repository in VS Code, and normally I am able to do that right there on GitHub, which would change to github.dev in this case. I should be able to compare these two scripts to show the changes. So in this case, I will select the number of steps per execution and make the dataset divisible by that, with this number in mind, divisible by the batch size. And after that, I specify this parameter when doing the model.compile, calling this function, both for training and evaluation. And with that, I should be able to run faster. Instead of 3 milliseconds per epoch, I should be able to run in under 200 microseconds, I guess. So we are compiling the graph again, because now it's a different graph with this additional loop on the device to process multiple batches in a single run. Every time I process a batch here, I make a gradient step and update the weights. But there is another parameter that will make the model process multiple batches before making a gradient step. And this parameter is called gradient accumulation. It's also described in the README file. Which is then used to, when configuring the system, you will use this gradient accumulation so that several batches are processed and the gradient from several batches is accumulated before applying this gradient to the weights of the model. This is helpful when you are running data parallel with multiple replicas and you want to reduce the overhead of communications between the replicas when doing your weight updates. If you do your weight updates very frequently, every batch, for example, and the model runtime is relatively small, then the overhead of communications will hurt your performance. You will see suboptimal scaling efficiency because of that. So you use 2 replicas, but the throughput is increased only 1.5 times. And running with a higher number for gradient accumulation will help. And another thing that is shown in this tutorial is pipelining, which is spreading the computational graph across more than one IPU. For models that are large, for example, BERT large, we distribute the computation, the layers of the model across, say, 4 IPUs. And then the layers, the first section of the layers will be allocated to the first IPU, the second will go on the next IPU, and so on. And then the pipeline will try to eliminate the computational bubbles so that the overhead of pipelining is small. You can see that when we start pipelining and ingest the first batch here, the first IPU gets busy immediately, but the IPU number 2 and 3 wait and stay idle until the activations arrive to them. But then moving forward, we can actually leverage those IPUs and process the following batches as we do the backwards pass with the previous batch. So the inefficiency is relatively small, especially if you process multiple batches in a single execution of the engine. For example, if I use 4 IPUs and I process 64 batches, accumulating the gradients, then the overhead will be relatively small. And pipelining can be enabled by either manually annotating the function that builds the computational graph with these pipeline stage constructs that will put specific layers on into specific pipeline stages, or it can be done also separately, where you have a model that is described in a separate file. Maybe you use a pre-built ResNet 50 from Keras. You can still pipeline a model like that by processing the layers with a separate function and associating different layers with different pipeline stages. And we have a tutorial for that as well. I think it should be described, not in the tutorial, it should be described in the TensorFlow Keras documentation. Let me make sure. Yeah, I think this tutorial covers replication and pipelining when you annotate the script. And I also wanted to mention that in order to run with multiple replicas on the IPU, you simply ask for more IPUs. If I compare, for example, the faster script here with the replicated execution, I have this additional parameter, which is the number of replicas I am running with. And I need to correct the divisibility accordingly. And then the only change after that is me asking for 2 IPUs instead of 1. And then Poplar will take care of running data parallel and enabling communications between the replicas for you after that. So this is what I wanted to say about Keras and TensorFlow. So I hope this will be enough for you to start running your scripts on IPUs with TensorFlow 2 and Keras. And we have quite a few examples and guides or documentation pieces that go into much more detail for different frameworks. Well, TensorFlow and PyTorch, I should say. TensorFlow 2 mostly. So a quick start on how to put your model with TensorFlow 4, which is basically what we have in the tutorial, and some more in-depth optimization techniques and tricks. Any questions so far, and were you able to run the demo scripts? And meanwhile, let me ask the this thing. The replicated example. So I wanted to use the TensorFlow tutorial to show the value of using the steps per execution, as you can accelerate your trainings significantly with that, especially for smaller models. For very large models, I think steps per execution will result in a smaller advantage because, well, every execution, every engine run will take a lot of time relatively to calling it and moving data to it. But still, it is a useful technique, as we are finding. And we have about 23 minutes left, I guess. With that, I wanted to mention, say a few words about PyTorch and how PopTorch can be used to execute PyTorch scripts on the IPU. So PopTorch obviously stands for Poplar Torch. It is a set of extensions to enable PyTorch on the IPU, supporting both inference and training. And it's structured as wrappers for inference and training, for model wrappers that extract the graph, the computational graph from your model, and can be used to pipeline a model across the IPUs or run with multiple replicas data parallel as well. The process is quite straightforward in terms of what's happening, what PopTorch is doing. So we obviously define a model using PyTorch. We create these wrappers, training model and inference model wrappers. And then PopTorch extracts the graph using PyTorch dispatcher and takes care of compilation and the backwards pass on the IPUs. A typical program, when we say port a PyTorch script from GPU to the IPU, will be shown on this slide. The main two lines are these two. So we use this PopTorch.training model, and it takes my training model as an argument. This training model has loss computation being a part of the forward pass. With this, PopTorch will extract the forward pass graph and will build the backwards pass for you, so that in the training loop, you do not have to do the backwards pass and the gradient step explicitly. It is done with this call to training_model for you. And then similarly to we use PyTorch inference model to wrap the forward pass, not necessarily with loss. So in this case, I have it without loss computation, just predictions being computed during inference. And it's called in a similar way to the loop on GPU. And optionally, I can detach from device to release the IPU that I used to run the training graph, so that I reuse the same IPU to run inference on it. And then these changes, the device iterations, is the same as steps per execution in TensorFlow. Device iterations is a loop on the device that will process, in this case, 50 batches with a single call to the training model. And then we have special data loaders that can produce multiple batches of data for me, so that when I run this model, I will ingest and have 50 batches ready to go. PyTorch has a few data loaders that operate and run asynchronously. For example, when your host and data preparation takes some significant time compared to the execution of the model, you can overlap the host computation with the IPU computations, so that the overhead of doing the data preparation is reduced and the overall throughput is better on the IPU. Some of the options are mentioned for PyTorch, are mentioned in our documentation, and there are device iterations, replication factor, which is used when you run with multiple replicas, and a few others there. And the tutorials are linked on this slide. Basically, everything under the tutorials PyTorch repository. Basics is what we start with, and then there is mixed precision dedicated to running with FP16 and doing some accumulations in FP32 maybe. Then efficient data loading, which discusses asynchronous data loaders, for example, and pipelining. So let me go to those repositories and work from there. So instead of TensorFlow 2, I go into PyTorch basics, and there is a README file that describes the tutorial. It is also structured with this notebook, which can be easier to run in some cases, but on this ACES system where you SSH into, it can be an issue. You cannot tunnel the Jupyter Notebook port efficiently, or at least I haven't tried that. So you can use walkthrough code only for that. And let me run that. This notebook will describe what we're trying to do and the changes needed to port a model to the IPU. So let me navigate to that directory and then go into PyTorch basics. In here, I will have requirements that I will need to pip install. And then I will execute the walkthrough Python script. I guess it was with recent changes to the dependencies that it became like this. We'll make sure it runs in the next SDK release seamlessly. And the next SDK 3.4 is coming soon. It is expected by the end of October. So while it is running, the notebook describes, again, PyTorch as a set of wrappers that extract a computational graph, put it through PopArt and then Poplar libraries and Poplar to compile it. And then the changes to the code are all listed here. For the first section, we list the code without changes, and then we do the preparation for IPUs. We instantiate this options object, which can contain things like device iterations or number of replicas. We use the options to create a data loader, which mimics the PyTorch data loader API to a large extent. And then we create a training model object using the model with loss, options, and the optimizer. And by the way, PyTorch offers optimizers that perform better in a few cases on the IPU. So it would make sense to use PyTorch optimizers instead of Torch plain optimizers if performance is what you're after. Then the training loop is similar to TensorFlow, with data being streamed to the IPU for a given number of device iterations. And then we update the weights, and at the end of that loop, we copy the weights to the host, to the CPU. And then the training loop is pretty intuitive. We just call the PyTorch model, which does gradient updates for us. Sorry, weight updates and gradient steps. And then we can detach from the IPU to reuse the device for evaluation, for inference. We can also save the model state using the standard torch.save function. And the evaluation will be structured with PyTorch inference model wrapper that will take the forward pass of the model and do the same operation, basically extract the graph, compile it so that we can run it in a loop on our data set, just as you would typically do in PyTorch. And then it describes the rest of the steps that run a specific model with a specific example to make sure that the predicted class of an image after training a model on the IPU and then training a model similar architecture on the CPU produces similar results, identical architecture, I should say. And it describes some of the options that you can use here: device iterations, replication factor, random seed, to make the runs deterministic and reproducible. And then use IPU model in cases where you want to run on a simulator, not on the actual IPU, but actually on CPU with all the IPU specific APIs. Any questions so far? And were you able to run this tutorial and take a look at the code with me? So the mixed precision tutorial discusses that when you run in half precision, when you run your matmals and overall arithmetics in FP16, you can see higher throughput, so lower overall time to train. There is potentially an issue with numerical stability that you can address by using loss scaling and stochastic rounding, which are both supported on the IPU. Loss scaling as automated loss scaling, or loss scaling by a fixed factor, and stochastic rounding is hardware accelerated on the IPU, and this is basically randomly rounding the value when adding two values together to the highest or to the lowest based on the distance. The probability will be based on the distance to the highest or to the lowest representable number. And then to train a model in a half precision, I will I will set up the parameters of the graph. I will cast the model weights to half precision. I can selectively cast specific layer weights to half precision, and I want to make sure my inputs are half precision as well. So very typical operation for PyTorch. And then among the options, I want to typically enable stochastic rounding and use maybe half precision partials. And partials in this case, meaning the results of multiplications when doing matmols. So my matmols will run completely and in FP16, or optionally, I will accumulate to FP32, and then after a matmol, it will be, the value will be casted to FP16 for storage. So this is the mixed precision in a nutshell. And then data loading. This tutorial discusses the options available to optimize the time a data loader takes to prepare the data and to stream the data to the IPU. And some of the options are asynchronous data loaders that are available with PyTorch as a part of the repository. And it is described here. So in this case, the data loader will prepare the batches for the next execution of the binary of the model on the device asynchronously while the previous set of batches is being processed. And then gradient accumulation is a parameter for that, because we want to account for not only the batch size, but also the number of batches we accumulate across replication as well, and device iterations. So the data loader prepares all this data, a multiple of all these factors should be used to produce the batches, the data structures, tensors of the proper size. So it has some basic guidance on how it works and what to do if you feel the throughput is too low. Discussions like where to look at device iterations versus gradient accumulation, which affects the global batch size for a given number of replicas. And there is a set of scripts that you can execute here to experiment with different device iterations and replication, as well as using the asynchronous mode in the data loader to produce batches while the accelerator is processing the previous batch or set of batches of data. So with this, you can optimize your performance and run faster in terms of time to train or time per epoch. So unfortunately, I do not have a lot of time during a short workshop to go into a lot of details, but I encourage you to try these examples and tutorials out, and feel free to ask any questions as you run those. If you have any ideas how this can be useful for your project, for your use case, and whether, well, should you encounter an issue that you can not find an answer for in the documentation or in the community channel, please feel free to reach out to me as well. A couple more minutes, I wanted to use the remaining ones, to point to a couple of interesting projects and repositories that we have. Graphium, for example, is a collaboration between Graphcore, Mila, and Valence, a drug discovery startup in Montreal. This is a repository that uses GNNs to help you build pipelines of data preparation, data pre-processing, featureization for molecules that can be then used to train a GNN to predict some kind of property of a molecule. This is based on our work when we were preparing the submission for the Stanford Open Graph Benchmark large-scale contest, which we, this collaboration, Valence, Mila, Graphcore took the first place in that contest, outperforming in terms of accuracy teams from likes of NVIDIA and Microsoft, which we are very proud of. So this this repository can give you a good start into drug discovery with GNNs if you're working on that. And overall, we've been investing a lot in supporting PyTorch geometric, which is the leading framework now for graph neural networks. So we support many operations here out of the box. And I also wanted to mention that we have this set of tools that we call Pop Vision to help you optimize performance and see whether there are any bottlenecks with your model, both on the CPU side, say data preparation, or on the IPU side. Maybe there is an operation that takes unexpectedly many cycles to run, or is not optimally balanced across the cores. So Pop Vision tools, which again can be downloaded freely, give you that visibility. And we have a set of documents covering those, how to produce profiles, how to analyze those using those visual tools, how to do that programmatically. And you will have these slides for reference. So on this slide, I show how I can extract a profile from the same walkthrough for PyTorch basics that we just ran together. And then the IPU side, the graph analyzer, as we call it, shows you memory usage by the tile on this view. And then liveness report shows the same thing, but by program step. So if there is a specific program step that takes too much memory, like this convolution, maybe, you can take a closer look at what variables are being created and how the memory is used. And then execution trace here on the left gives you visibility into what's happening cycle after cycle across all the tiles on the vertical axis throughout the execution of the graph. So you will have a flame chart with all the operations shown here, and the BSP trace with, say, computation shown in red. So a bunch of cores in this case doing computation, running compute vertices, I should say. And then blue is data exchanges between the cores, and yellow is synchronization. So if there is too much yellow, probably I'm not using all my cores efficiently enough, because most of the time they are waiting in this case. So maybe I should be running with a larger batch size. Question on Pop Vision. Are there tutorials on how to use Pop Vision for mitigating out-of-memory errors, or how to use Pop Vision to get more performance? Yes, these are great questions. So on this slide, I am using this option, allow out-of-memory set to true. In this case, even if the compilation ends with an out-of-memory error, I still will be able to view memory profiles and see which tiles or which program steps result in this out-of-memory error, and maybe optimize for that. This is quite useful when you're running across, say, more than one IPUs, and you want to balance memory usage between the IPUs. So moving layers between the IPUs manually. And in terms of performance, similarly, this will be the view that you want, and the documentation is available on our website. Let me see if I can Pop Vision. Just among the software documents, there is the Graph Analyzer user guide and the System Analyzer user guide, and some programmatic analysis details as well. So the Graph Analyzer will address your questions, and it will cover the out-of-memory situations as well. Not only this, in addition to the user guides for Pop Vision, we also have these optimization guides for memory and performance, and then a subsection for convolutions and metmols as well, both for PyTorch and TensorFlow. So thanks a lot for this question. And we also have a few tutorials dedicated to Pop Vision tools, tutorials that use Pop Vision tools to extract and show profiles when pipelining, for example, or using in-feed, out-feed APIs to optimize performance, data streaming performance for TensorFlow. And a couple more screenshots from the Graph Analyzer show multiple IPUs side by side. In this case, I am comparing different runs of the program when trying to optimize something from one run to the other run. And I will see memory usages as well here. And then the execution trace when I am pipelining, for example, across 4 IPUs can be viewed and would look something like this. And this is a screenshot from a tutorial. On the system side, you will see the threads, the CPU threads being executed to pre-process the data for the IPU. And here you will see any bottlenecks potentially on the host side, on the CPU side. This can also be used to track things like numerical stability or weights for specific model layers. In this case, these are the convolutional layer weights that during epoch 0 are initialized randomly, and then as we move forward up to epoch 9, there appears some kind of structure among those weights, and they are more within the representable or comfortable range for FP16, for example. So these are all the slides that I have. My email address is here. So alext@graphcore.ai. The slides will be shared with you, and I guess Zhenhua will be published on the event page as well.
Thank you, Alex. Yes, the slides has been posted on our HPRC website. If you go to our website and click on the training tab, under courses, we have Graphcore IPU training courses, and if you click on view details, you can find these presentation slides there.
Thank you very much. So there is a question in the chat. Justin is asking if IPUs have something similar to NVIDIA CUDA's occupancy in terms of shared memory per block. We do not have that, and I guess the closest analog will be this execution trace. So it can be analyzed after an execution, and since everything is compiled statically, you will have predictable executions in a typical machine learning case. So you can analyze that offline and then make changes or conclusions about your graph. Even when logic statements, iterations until convergence are unknown and wildly varied. So that's an interesting case. In TensorFlow, we do support conditionals where you execute one graph or the other graph based on state of a variable. We do support that in the lower level framework, Poplar as well. In PyTorch currently, we do not support that because the graphs are traced only once. So all the ifs and conditionals are extracted during that compilation and will not change with the subsequent runs. If you are running into a dynamic execution case, this static compilation will not be ideal for you. In many cases, this can be done with things like padding, for example, for different sequence lengths. If this is a different number of iterations that you're after for like something, if you are running multiple loops and you determine convergence when the engine is running, again, it is possible in TensorFlow, and in PyTorch, I think we still do not support that. But if you think, well, there is something we can do together, if you feel there is a project that can inform our software roadmap, please feel free to let me know. I'm very happy to discuss this. Great. Thank you. Thank you very much. Appreciate your time, and thank you for joining us today.
Thank you, Alex. Thank you for the excellent short course, and thanks everyone for attending. And we have our HPRC help desk email. I will type it in the chat. Help hprc.tmu.edu. If you have any questions about the ACES cluster and the IPUs, if you want to use our cluster, you can send us an email. And also, if you have questions to Alex, you can also send it to us, and then we can forward that email to Alex, or you can just directly send the email to Alex. Okay, thank you very much.